What if I told you that the greatest engineers of ancient Rome defeated the laws of physics 2,000 years before we formulated them? The eternal city, shining at the center of a vast empire, could not exist without water. But how could billions of liters of the purest ice-cold liquid be brought to 1 million inhabitants across mountains and valleys without the use of powerful pumps? This task seemed impossible, and the key to solving it lay not in magic, but in astonishingly accurate calculations. Knowledge of geodesy and architectural genius that we cannot always replicate today. Roman aqueducts are not just pipes. They are monuments to the human mind that supplied entire cities with water for hundreds of years. Watch the video to the end to find out how ancient builders calculated the ideal slope with millimeter precision and why a 1-degree error could spell disaster for the entire water supply system. Are you ready to learn how simple water became the main symbol of power, order, and civilization? By the end of the 1st century BC, Rome could no longer be called just a city. It was a true metropolis of the ancient world, with a rapidly growing population approaching 1 million people. There was a catastrophic shortage of old water sources, wells, springs, and even the Tiber River. They no longer provided not only comfort, but also the basic survival of such a large number of people. The Tiber was polluted with sewage, garbage, and craft waste. Wells quickly dried up or provided water of dubious quality. Under these conditions, the issue of water supply became a matter of political stability. A city without water was doomed to epidemics, unrest, and decline. That is why the Romans made water the basis of their state strategy. The first aqueducts were built not only for convenience, they were a powerful symbol of Rome's superiority over the surrounding world. The ability to carry clean mountain water for tens of kilometers and deliver it directly to the city was seen as proof of cultural and technical leadership. Rome contrasted itself with the barbarians who drank water from muddy rivers and swamps. Clean water was vital for maintaining sanitation in densely built-up areas. It was used to wash streets, sewage systems, and public toilets. But it played a particularly important role in the operation of the baths. Public baths were not just a place to wash, but the center of the city's social, political, and cultural life. Their operation required enormous amounts of water, which was constantly being renewed and drained. The first Roman aqueduct, the Aqua Appia, was built in 312 BC. Its appearance was a real engineering revolution. However, it ran almost entirely underground. This solution made it inconspicuous to the population, but provided protection from enemies and sabotage. Water flowed continuously, regardless of the weather or season. Over time, Rome's ambitions grew, and with them, the number of aqueducts. Their routes became longer, and their structures became increasingly bold and monumental. Underground channels gave way to majestic arcades that crossed valleys and plains. These structures ceased to be mere engineering projects and became architectural symbols of the state's power. Public water consumption became part of political propaganda. Fountains, pools, and thermal baths demonstrated the authorities' concern for their citizens. An abundance of water meant prosperity, order, and stability. The emperor under whom a new aqueduct was built automatically strengthened his reputation and support among the population. The Romans also attributed medical significance to water. They believed that clean running water brought health and vitality. Stagnant water, in their opinion, was a source of disease and decay. Therefore, the water supply system was designed so that the water was constantly moving and did not stagnate. Aqueducts also changed private life. Wealthy homes began to connect to the water supply network. Water was supplied to atriums, gardens, and private baths. This became a source of envy and a clear indicator of social status. However, access to water from the aqueduct was strictly regulated. This required official permission, which emphasized social inequality. The engineering task was extremely difficult. It was necessary to find a source of clean water at a considerable distance from the city to avoid contamination, while maintaining a minimal but constant slope of the canal. An error in the calculations could lead to the shutdown of the entire system. Sources in the foothills where the water was cold, clean, and rich in minerals were considered ideal. Roman engineers used only the force of gravity, without pumps or mechanical devices. This required incredible precision and a deep understanding of the terrain. It is thanks to these solutions that many aqueducts continued to function for centuries. Thus, aqueducts became a true cornerstone of Roman civilization. They provided Rome with a level of comfort, hygiene, and social organization that was unattainable for most ancient cities. Water became the foundation of health, power, and imperial grandeur. We are very interested in hearing your opinion. Which engineering system of ancient Rome do you think had a greater impact on the development of civilization? Aqueducts or roads? Write about it in the comments and be sure to subscribe to the channel so you don't miss other historical investigations. What if I told you that the main secret of Roman aqueducts lies not in giant arches or concrete, but in a tiny, almost imperceptible slope? The main task that Roman engineers had to solve was to create a constant and stable flow of water without the use of pumps, mechanisms, or external energy. The entire system had to operate solely by gravity. This required maintaining the ideal slope of the canal. It had to be steep enough so that the water would not stop, but at the same time gentle enough so that the flow would not destroy the inner walls of the aqueduct. It was an extremely delicate balance, where an error of a fraction of a percent could lead to catastrophic consequences. The Romans concluded that the optimal gradient was approximately 1/3000 to 1/5000. This means a drop of only 1 meter for every 3 or even 5 kilometers of travel. Such a slope is practically indistinguishable to the human eye, but it ensured the perfect flow of water. Maintaining such precision over tens and hundreds of kilometers was an incredibly difficult task. To do this, the Romans developed their own surveying instruments, many of which had no analogs in the ancient world. These devices allowed them to measure the smallest differences in elevation with remarkable accuracy. One of the main instruments was the chorobatus. It was a long wooden level with a carved groove that was filled with water. By the water level, engineers could determine even the slightest slope of the surface and adjust the direction of the canal. In addition to the chorobatus, other instruments were used, such as the diopter, which allowed for accurate sighting at a distance. All measurements were taken manually, without optics or complex calculation formulas. Success depended on the experience and attentiveness of the engineers. If the slope was too steep, the water began to flow too quickly. This led to erosion of the inner lining of the canal, damage to the protective layers, and accelerated wear of the entire system. In the long term, such an aqueduct would collapse. If the slope was too small, other problems arose. Water stagnated, algae began to grow in the canal, and dissolved minerals settled on the walls. Over time, this led to the narrowing of the canal and its complete blockage. Even a small error in calculations at the beginning of construction could turn into a huge problem tens of kilometers later. It was almost impossible to correct such an error at a late stage. Therefore, the design process took a long time and required exceptional precision. Engineers had to take every detail of the landscape into account. Hills, valleys, rock types, and soils all influenced the route of the aqueduct. Sometimes the route was deliberately lengthened to maintain the required slope, rather than going straight. For this reason, the Romans sought to lay most of the aqueduct underground. Underground channels were better protected from contamination, evaporation, and temperature fluctuations. In addition, they were less vulnerable to damage and enemy attacks. The underground location also ensured a more stable water temperature. Even on the hottest days, the water remained cool, reducing the risk of algae and bacteria growth. This had a direct impact on the quality of the water supply. Special vertical shafts, known as guideposts, were used to construct the underground sections. They allowed builders to work on several levels at the same time, speeding up the tunneling process. These shafts served other purposes as well. They provided ventilation, removed rock, and provided access for future inspections and repairs. Many of them were used for centuries after construction was completed. Thus, the ideal slope of the aqueducts was not a coincidence or luck. It was the result of centuries of experience, observation, and a deep understanding of the interaction between earth and water. In the next chapter, you will learn how the Romans were not afraid to build aqueducts through mountains and deep valleys, and what unusual methods they used to overcome these obstacles. You've definitely never heard of this unique secret of Roman engineers. When the Romans built aqueducts stretching for tens and hundreds of kilometers, they inevitably encountered serious natural obstacles. One of the most difficult of these were deep valleys and ravines. In such places, it was impossible to maintain the smooth slope of the canal, which was vital for the flow of water. Building a classic arcade in these conditions was often either technically impossible or way too expensive. The arches would have to be huge and the foundation would have to be super strong. That meant years of work and crazy costs. This is where Roman engineers got really creative. In such cases, they used an ingenious and, at first glance, paradoxical solution known as an inverted siphon, often referred to as a lead siphon. This solution seemed to be a direct violation of the usual laws of water supply. After all, water should have risen upward, which contradicted the principle of gravity. However, the Romans understood the properties of water and pressure very well. They knew that liquid in a closed system behaves differently than in an open channel. It was this knowledge that formed the basis of the siphon. It was an example of how theory was put into practice. The essence of the method was that water was deliberately directed down pipes to the deepest point of the valley. Strong lead or ceramic pipes were used for this purpose. As it descended, the water gained pressure, creating a powerful force. Under the action of this hydrostatic pressure, the water then rose through the pipes to the opposite slope. It did not need pumps or mechanical devices. The pressure did all the work on its own, using only gravity and the closed nature of the system. This technique made it possible to cross deep valleys without building giant bridges. This significantly reduced the time required to construct an aqueduct. In addition, engineers were able to lay routes where it had previously been considered impossible. Of course, the use of lead pipes was an extremely expensive undertaking. Lead required high costs for extraction and processing. However, compared to the large-scale construction of arcades, it often proved to be a more cost-effective solution. The siphon began with a storage tower located at the edge of the valley. In this tower, water was collected and directed into pipes. It was here that the initial pressure was created, which started the whole process. The water then rushed down the pipes, accelerating with every meter. At the lowest point of the valley, the pressure was at its maximum. Therefore, the pipes in this place were made especially thick and carefully reinforced. Any mistake could lead to a pipe rupture and water loss. Repairs in such conditions were difficult and dangerous. This required constant monitoring and highly skilled workers. On the opposite side of the valley was the second tower. It received water and served as a pressure relief point. Here, the flow returned to the usual open channel. After that, the water continued its journey along the aqueduct with the usual gravitational slope. For the townspeople, this transition was invisible. But behind the scenes, it was a real engineering marvel. Despite their effectiveness, siphons had serious limitations. The main problem was the high pressure exerted on the pipes. Even a small crack could lead to an accident. In addition, lead wore out over time. The pipes required regular inspection and repair. This made the operation of siphons difficult and expensive. There was also a physical limitation. Water could never rise above the point from which it began to flow. Pressure losses due to friction against the pipe walls were inevitable. For this reason, siphons were used only in extreme cases. If it was possible to build an arcade, the Romans chose it. Reliability was always valued above spectacular solutions. The most famous example of an inverted siphon is considered to be the aqueduct system in Lyon. 9 lead pipes laid parallel to each other were used there. They withstood pressure that is considered very high even by modern standards. This system worked for decades and supplied the city with water without interruption. It became proof of how far Roman engineering had advanced. Even today, such solutions command respect. In general, the Romans preferred arcades for their simplicity and durability. But the very existence of siphons shows that they knew how to adapt to any landscape. Their engineering knew no dead ends. Be sure to like this video if you didn't know about this amazing secret of Roman water supply. And don't forget to subscribe to the channel so you don't miss any new videos. What you are about to learn will change your perception of Roman construction. The amazing durability of Roman aqueducts, temples, and bridges is explained not only by the skill of engineers, but also by the use of one of the greatest technological secrets of antiquity, a unique concrete that still has no full-fledged analog. The Romans did not limit themselves to simple stone masonry as we understand it today. They created their own composite building material, which they called opus cementitium. It was this material that became the prototype for modern concrete and allowed Roman architecture to go beyond the capabilities of most ancient civilizations. This material was a mixture of aggregates, lime, and a binder. Unlike ordinary mortar, it did not simply bind the stones together, but formed a single monolithic mass. This structure made the structures much more resistant to stress and time. The key component of Roman concrete was volcanic ash, known as pozzolan. This ash was mined in volcanic areas of Italy, especially in the vicinity of Naples. The Romans noticed that when pozzolan was mixed with lime and water, it produced a material with unusual properties. The most striking thing was that this mixture could harden even underwater. Unlike most building materials of the time, Roman concrete did not deteriorate in a humid environment, but on the contrary gained strength. This property made it a real revolution in construction. It was thanks to the hydroactivity of pozzolan that the Romans were able to build durable ports, breakwaters, bridges, and foundations in coastal areas. This was especially important for aqueducts, as constant contact with water would destroy any less durable material. The main load-bearing structures of aqueducts, such as arches and supports, were built of stone or brick. However, the internal water channel, called a specus, was lined with pozzolan concrete. This created a strong and watertight shell inside the entire system. The smooth surface of the concrete reduced the friction of the water against the walls of the channel. This allowed the water to flow evenly and maintain its pressure over long distances. In addition, it reduced the accumulation of sediment and dirt, which made maintenance easier. The inner walls were often covered with an additional protective layer on top of the concrete. This was a waterproof plaster known as opus signatum. It consisted of lime, fine sand, and crushed ceramics, which made the coating particularly dense and durable. This layer served as the final barrier against leaks. Even if the main structure developed microcracks over time, the plaster kept the water inside the canal. This multi-level protection significantly extended the service life of aqueducts. The use of pozzolan was of great strategic importance. Its extraction and transportation were controlled by the state. Volcanic ash was delivered from Italy to all corners of the empire, including North Africa, Gaul, and the Middle East. This made it possible to build strong and durable structures, even in regions with different climates and geology. Thus, a unified construction technology united the empire no less than laws in the army. The results of this approach are still impressive today. Many Roman aqueducts, bridges, and harbors have stood for over 2,000 years. They have survived earthquakes, wars, floods, and the rise and fall of civilizations. Modern scientists are still studying Roman concrete, trying to understand why it has proven to be so durable. Laboratory studies show that its structure differs from modern concrete at the microscopic level. There is a hypothesis that Roman concrete becomes even stronger over time. Seawater and minerals react with pozzolan, forming new crystalline compounds that strengthen the material from within. This self-repairing effect makes Roman concrete truly unique. That is why many modern engineers are trying to adapt ancient recipes for the eco-friendly construction of the future. We already understand what these grandiose structures were built from, but the next question arises. How did the Romans operate such a complex and extensive water supply system? In order for the entire water supply system to function like a perfectly tuned mechanism, water had to be distributed among various consumers in a strictly defined and well-thought-out order, rather than simply flowing into the city. The Romans understood that uncontrolled water supply would quickly lead to shortages and chaos. That is why a complex hierarchical distribution system was created, which began with water distribution towers known as castella. When the aqueduct reached the city limits, it did not discharge water directly into the street network. First, the flow was directed to a castellum, a massive stone structure, often multi-level, which served as a reservoir, distribution hub, and pressure reducer. This protected the city's pipes from destruction due to excessive pressure. Castella played a key role in water management. Inside these structures, the water slowed down and settled, allowing sand, silt, and small debris to settle to the bottom. This way, cleaner water entered the city network, which extended the life of the pipes and improved sanitary conditions. From the castellum, water was distributed in several directions through a system of lead pipes of various diameters. The size of the pipe directly determined the volume of water supplied. This allowed for precise flow control and prevented unauthorized connections. The first and main recipients of water were public fountains. They were located throughout the city and provided free access to drinking water for all segments of the population, including the poorest. Providing fountains was considered a vital social task of the state. The second priority was the thermal baths, or public baths. These complexes required enormous amounts of water for pools, steam rooms, and constant cleaning of the premises. Despite the high consumption, the supply of water to the thermal baths was considered vital, as they served not only a hygienic, but also a social function. Only after the needs of fountains and thermal baths had been met was water directed to the private homes of wealthy citizens. If there was not enough water, private consumers were the first to lose access. This system emphasized the priority of public welfare over personal comfort. Each private connection was strictly controlled. The pipes leading to the homes of wealthy Romans were sealed and had a pre-approved diameter. Unauthorized pipe expansion was considered a serious violation and was punishable by fines. This was an effective way to regulate consumption and prevent abuse. In addition, private users paid for the right to receive water from the aqueduct. Thus, water supply was partially transformed into a commercial service, the proceeds from which went to the maintenance and repair of the entire system. Water pipes known as fistulae were made of lead, as this metal was soft, easy to shape, and allowed pipes of any shape to be created. The joints were carefully soldered to minimize leaks. Despite the potential health hazards, there were simply no alternative materials with such properties in ancient times. The distribution system was designed so that the water was constantly in motion. Even in fountains, it did not stagnate, but continuously overflowed and drained into the sewer system. This prevented contamination and helped maintain sanitation in the city. Excess water that passed through fountains and thermal baths was used to wash streets and public toilets, and then sent to the sewer system. Thus, water supply and sewerage worked as a single entity. This multi-level and strictly regulated system was created to ensure the fair distribution of water. It served the interests of the majority of citizens and public needs first, and only then private luxury. It was this approach that allowed Rome to maintain a high level of hygiene and quality of life in a huge metropolis. Even the most ingenious system needs constant maintenance, and the Roman aqueducts were no exception. Maintaining this gigantic network was a separate, complex task that required enormous resources and an army of specialists. For this purpose, a special government service called Curator Aquarum was created, headed by a high-ranking official. His task was to monitor the condition of all aqueducts, oversee their repair, and prevent illegal use of water. Inside the aqueduct, or spicus, lime deposits constantly formed. This was inevitable, as the water came from sources rich in minerals. If these deposits were not removed, they could completely clog the canal. Special repair shafts, which we have already mentioned, were used to clean the canal. Workers descended into these shafts and used scrapers and tools to remove hard lime deposits that could reduce the flow capacity. Repair work was carried out continuously. Maintenance personnel monitored cracks, repaired leaks that could weaken the structure, and repaired damaged sections after floods or earthquakes. Funding for this system was multi-level. Some of the money came from taxes paid by the city's residents, and some came from water usage fees paid by private consumers and spa owners. However, the biggest problem was illegal connections. Many people tried to secretly tap into the main pipe to steal water, and combating such water thieves was one of the main tasks of the supervisory service. The lead used to make the pipes was a very valuable material. Sometimes the pipes were simply stolen to be melted down for other purposes, which required constant monitoring of the network. Ambushes and inspections of water carriers were commonplace. High fines were imposed for illegal connections, which served as a serious deterrent. Illegal use of water was not just theft, but a disruption of the entire system. As we will see later, it was not only aqueducts that were a complex system. In the next chapter, we will talk about another engineering marvel of Rome, their sewerage and drainage systems. The arch bridges that we see today among the ruins of Roman aqueducts were the most impressive, but far from the most common element of these systems. Their construction was used only in special cases when the aqueduct had to cross a wide lowland, ravine, or valley where it was impossible to maintain the necessary gravitational slope by other means. In most cases, the Romans preferred to run the channels underground or along low embankments. Arches were only necessary when the terrain left no other choice. That is why such structures were rare and extremely expensive, but at the same time as effective as possible. The main task of the arcade was to maintain a smooth and precisely calculated slope of the canal along which the water flowed. The aqueduct was located at the top of the structure, at ground level or slightly above, so that the water could flow by gravity without stopping or pressure drops. Each arch was calculated with remarkable precision. Engineers took into account the weight of the stone, water pressure, the height of the structure, and the characteristics of the soil. Even a few centimeters of error could lead to the collapse of the entire system, so the design process took a long time. The construction of the arches was one of the most difficult stages of the aqueduct's construction. It required a huge number of workers, well-organized logistics, and constant supervision. Massive wooden scaffolding was used to erect the arches, which held the stones in place until the structure was completed. The semicircular shape of the arch was not chosen by chance. This geometry allowed the load to be evenly distributed throughout the structure and transferred to the vertical supports. Thanks to this, the arch could withstand enormous weight without the use of metal elements. It was this shape that made Roman arcades incredibly strong and stable. Even if one arch was partially damaged, it could continue to bear the load without destroying the entire system. This was an important factor in their durability. The tallest arcades, such as the famous Pont de Gare in modern-day France, are still impressive in size today. They reached a height of almost 50 meters and a length of hundreds of meters. All this was built without cranes, concrete mixers, or modern technology. The stone blocks for such structures were fitted with exceptional precision. In most cases, they were not held together with mortar. Strength was ensured by the perfect fit of the stones to each other and the force of gravity, which compressed the structure even more. Each block was cut and processed by hand. The slightest inaccuracy meant that the stone could not be used. This required a high level of skill from the masons and strict quality control. These monumental structures served not only a practical function, they were a visible symbol of Roman power, order, and engineering superiority. The arches towered over the landscape and were visible for many kilometers. Anyone approaching a Roman city immediately understood what kind of civilization they were dealing with. The aqueduct was the first sign of the state's power, its ability to control nature and resources. At the very top of the arcade was a water channel. It was often covered with stone slabs to protect the water from dust, animals, and debris. The design included special openings for inspection, cleaning, and repair. Maintaining aqueducts was a constant task. Special workers regularly checked the condition of the canal, removed deposits, and monitored its tightness. This allowed the system to operate smoothly for decades. The arcades towering over valleys and plains were not just an engineering solution. They became architectural masterpieces, combining utility with aesthetics and scale. These grandiose bridges remained functional for centuries. Many of them were even used in the Middle Ages, and some are still partially functional today. This is the best proof of the accuracy of calculations and the highest quality of Roman construction. To achieve such precision in construction, Roman engineers needed equally precise tools. They had several key devices in their arsenal that allowed them to control slope and direction. One such tool was the gnomon, a vertical rod that cast a shadow. With its help, the Romans could determine the midday line and therefore the exact direction of the cardinal points, which was important for orienting the aqueduct route. The main tools for measuring height were a leveling rod and the aforementioned chorobatus. The chorobatus was a long wooden frame with a trough at the top into which water was poured. When the water in the trough was completely level, the engineers knew they had reached horizontal level. Then, using special wedges and calculations, they could set the required very small slope. Another key tool, the diopter, was used to determine direction and measure angles on the ground. The diopter was similar to a modern theodolite and allowed for accurate angular measurements. A spirit level, the simplest level, was used to dig tunnels underground, allowing workers to maintain a set depth and control the slope, even when working in complete darkness. Roman engineers also actively used plumb lines and cords to check the verticality of supports and the straightness of walls. These simple but accurate tools were the basis of all their large-scale projects. Surveying began long before construction started. Engineers walked the entire future route of the aqueduct, noting elevation changes, rocky areas, and places where bridges or tunnels would need to be built. Engineer, or architectus, was one of the most respected professions in Rome. He not only supervised workers, but was also responsible for all calculations and the final result, which placed a huge responsibility on him. It was these tools, combined with a deep knowledge of geometry and hydraulics, that allowed the Romans to create what we now call masterpieces of engineering. Aqueducts were only half of the great story of Roman engineering. To prevent the huge city from drowning in sewage, an equally well-designed and reliable sewage system was needed. Rome also achieved outstanding results in this area, creating one of the most famous and durable sewage systems of antiquity, the Cloaca Maxima. The Cloaca Maxima, or Great Sewer, was not just a simple drainage ditch. It was a monumental underground structure consisting of a huge stone canal. It became the central artery of the city's entire sewer system and is still partially functional today. Initially, the Cloaca Maxima was not created as a sewer system. Its first task was to drain the marshy area between the hills, where the Roman Forum later arose. Without this step, the city center simply could not have existed. Over time, as the population and construction grew, the canal was rebuilt and expanded. It became the main collector into which sewage from the entire city flowed. Thus, the original drainage structure became a full-fledged sanitation system. Not only household waste from homes ended up in the Cloaca Maxima, excess water from aqueducts, rainwater from the streets, and huge amounts of water used in the baths also flowed into it. Public baths discharged thousands of liters of water every day, which had to be quickly drained away. Even public toilets were directly connected to this system. Roman latrines were stone rooms with running water. Water constantly flowed under the seats, washing away waste and carrying it into the sewer system. The same water that came into the city through aqueducts was used for flushing. After use, it was not wasted but immediately sent to the sewage system. Thus, the water supply and sewage systems worked as a single closed mechanism. Rome's sewer system was extensive and multi-level. Small channels from private houses and streets flowed into larger collectors. These in turn connected to the main arteries leading to the Cloaca Maxima. The entire system operated solely by gravity. Engineers carefully calculated the slopes so that sewage would flow by gravity. This made it possible to do without pumps and mechanical devices. A constant supply of clean water from aqueducts was vital for the sewer system to function. This flow created a powerful current that prevented sewage from stagnating in the canals. Waste quickly passed through the city and was discharged into the Tiber River. The walls and arches of the Cloaca Maxima were built from massive stone blocks and Roman concrete. This construction ensured exceptional strength. The canals were so large that workers could move through them for inspection and repair. Regular maintenance was part of the city's infrastructure. Special services monitored the condition of the canals, removed blockages, and reinforced damaged sections. This allowed the system to function for decades and even centuries. Despite its sophistication, the Cloaca Maxima did not always cope with extreme conditions. During heavy rains or flooding of the Tiber, the sewer system could overflow, and part of the city would be flooded. Nevertheless, even with these problems, the existence of such a system was a huge step forward. Most ancient cities did not have a centralized sewage system at all, and simply dumped waste onto the streets or outside the city walls. Rome, on the contrary, tried to solve the problem comprehensively. Hygiene, sanitation, and waste control became part of state policy. This directly affected the health of the population and the sustainability of the city. Thus, water supply and sewage in Rome were two sides of the same system. Aqueducts delivered clean water, and the Cloaca Maxima effectively drained used water. Together, they created the sanitary foundation without which the existence of a huge ancient metropolis would have been impossible. The legacy of the Roman aqueducts cannot be overestimated. These structures not only supplied water to the Eternal City and other centers of the empire, but also became a benchmark for engineering thinking that defined the development of construction and hydraulic engineering technologies for centuries. Aqueducts turned water into a controllable resource and showed how infrastructure can become the foundation of a state's power. The Romans proved that water could be delivered over vast distances without the use of complex mechanisms. Their solutions were simple in principle, but incredibly precise in execution. It was this combination of practicality and scale that made aqueducts a model to be emulated. After the fall of the Western Roman Empire, many aqueducts gradually fell into disrepair. Without centralized authority and regular maintenance, parts of the systems were destroyed or abandoned. However, some of them continued to function for many years, albeit not at full capacity. For the new rulers and city authorities, restoring the aqueducts became an important task. They understood that control over water meant control over the city. Where the Roman water supply system was preserved, life remained more stable and organized. Many European cities of the Middle Ages grew directly on the ruins of Roman settlements. Their inhabitants often used the surviving sections of aqueducts without fully understanding how they worked. To the people of that time, these structures seemed like creations of ancient civilizations of an almost mythical level. The huge arches towering over the landscape were perceived as traces of the activities of giants or forgotten gods. Roman engineering inspired awe and fear, emphasizing the gap between ancient and medieval knowledge. During the Renaissance, interest in the ancient heritage flared up with renewed vigor. Scientists, architects, and engineers began to carefully study Roman texts and surviving structures. Aqueducts became the most important object of this research. Renaissance engineers did not simply copy forms, but tried to understand the logic behind Roman solutions. They studied slopes, arch proportions, and masonry methods. Based on this knowledge, new water supply systems were created for growing European cities. In Spain, France, and Italy, you can still see Roman aqueducts that amaze the imagination with their condition. The Pont de Gare in France and the aqueduct in Segovia have become symbols of technical perfection and precision in calculation. These structures demonstrate how sophisticated Roman masonry techniques were. The stone blocks are perfectly fitted together, and the structure itself is designed to withstand centuries of stress without serious damage. Modern engineers studying Roman aqueducts are still amazed by their accuracy. The Romans worked without laser levels, satellite measurements, or computer models. All calculations were based on experience, observation, and practical experiments. Their success shows that engineering is not only about technology, but also a deep understanding of materials, nature, and the logic of processes. The Romans knew how to use a minimum of resources to achieve maximum results. Aqueducts became a powerful source of inspiration for the development of hydraulic engineering. The principle of gravitational flow, which was the basis of Roman systems, is still used today. Modern water pipes are still based on the same basic laws of physics. Roman engineers proved that large-scale projects can be both practical and aesthetic. Their structures were not hidden underground, but became part of the landscape, emphasizing man's power over the elements. These systems outlived not only their creators, but entire eras. They served people centuries after the fall of the empire, proving that quality infrastructure is an investment in the future. Today, Roman aqueducts are not just historical monuments. They are living textbooks of engineering thought that continue to teach architects and builders. They clearly show how intelligence and discipline can subdue the forces of nature. Aqueducts remind us that the development of society is impossible without well-designed infrastructure. Water, roads, and sewage systems have always been the foundation of stability and growth in cities. Ultimately, aqueducts are not just stone pipes for water. They are monuments to the human mind, striving for order, cleanliness, and sustainability. They have become the embodiment of the idea of civilization, carved in stone and concrete. We have seen that Roman aqueducts are not just pipes, but complex integrated systems that required incredible precision in calculations, knowledge of geology, and unprecedented quality of construction. Their secret was not magic, but the perfect slope, the strength of porcelain concrete, and the courage to apply innovative solutions such as the inverted siphon. They truly conquered gravity, using its own laws to water the greatest city of antiquity. What modern engineering structure do you think can be compared in significance and complexity to the Roman aqueducts? Share your opinion in the comments and be sure to subscribe to our channel so you don't miss out on new research into the great achievements of the past.